Welcome to this scientific lecture on the physical and chemical transformations occurring during lasagna preparation. Today we will examine the complex interplay of heat transfer, polymer chemistry, and biochemical reactions that transform raw ingredients into a structured, flavorful dish. Lasagna represents an excellent model system for studying three fundamental processes: layered heat transfer through heterogeneous materials, starch gelatinization and moisture absorption in pasta sheets, and protein denaturation coupled with lipid phase transitions in cheese. Let me pose our first scientific question. Why does lasagna require such precise temperature control and cooking time? The answer lies in the simultaneous optimization of multiple rate-dependent chemical and physical processes. The answer is that we must achieve complete starch gelatinization, adequate protein denaturation, sufficient moisture redistribution, and optimal Maillard reaction products, all within a narrow temperature and time window. Let us begin with heat transfer. Lasagna consists of alternating layers with dramatically different thermal properties. Pasta sheets with thermal conductivity, approximately 0.5 watts per meter Kelvin, cheese with conductivity near 0.3, and sauce with conductivity around 0.6. Let's graph y equals 2 to the x. The first step is to create a table of values. A good strategy is to always choose x equals 0 and x equals 1, because they give you simple values to work with. This diagram illustrates the layered structure. Heat flows downward from the oven at approximately 180 degrees Celsius through these layers of varying thermal resistance. The heat flux is governed by Fourier's law, Q equals negative K times the temperature gradient. Where Q is heat flux in watts per square meter, K is thermal conductivity, and dT by dx is the temperature gradient. Due to differences in thermal conductivity, significant temperature gradients develop across each layer. The cheese layer, with lowest conductivity, acts as an insulating barrier. This graph shows temperature as a function of depth. Notice the steeper gradients in cheese layers due to lower thermal conductivity. The temperature decreases from 180 degrees at the surface to approximately 60 degrees at the bottom initially. Next, we examine the molecular transformation of starch. Pasta sheets contain approximately 70% starch by dry weight, primarily amylose and amylopectin. Here is our second question. What happens at the molecular level when starch granules are heated in the presence of water? The answer involves a phase transition. At temperatures between 55 and 80 degrees Celsius, starch granules absorb water, swell to several times their original volume, and the crystalline structure breaks down as hydrogen bonds between amylose and amylopectin chains are disrupted. This schematic illustrates the three stages. The native granule at room temperature is compact and crystalline. Upon heating with water, it swells dramatically. At higher temperatures, complete gelatinization occurs with full disruption of crystalline regions. The volume increase is substantial. Swollen volume equals initial volume multiplied by a factor of 5 to 10, depending on starch type and water availability. This plot shows viscosity versus temperature during gelatinization. Notice the dramatic increase between 55 and 95 degrees Celsius. This viscosity increase is what gives cooked pasta its characteristic texture. The pasta sheets must absorb approximately 100 to 150% of their dry weight in moisture from the sauce. This hydration is essential for achieving the desired al dente texture. Next, we analyze the transformations in cheese layers. Cheese contains approximately 25% protein, primarily casein, and 30% fat in the form of triglycerides. Our third question: what molecular changes occur in cheese proteins and fats during heating that cause the transition from a solid to a semi-fluid state? The answer involves two simultaneous processes. First, casein proteins denature as thermal energy disrupts tertiary and quaternary structures. Second, fat crystals undergo solid-liquid phase transition with melting points between 30 and 40 degrees Celsius. This illustration compares solid and melted cheese at the molecular level. In the solid state, proteins maintain organized structures shown as white circles, and fats are crystalline shown as yellow ellipses. After heating, proteins denature into random coils, and fats form liquid droplets. The thermodynamics are described by Gibbs free energy, delta G equals delta H minus T times delta S. At elevated temperatures, the entropy term dominates, favoring the disordered denatured state. These curves show the percentage of denatured protein in magenta and melted fat in cyan as functions of temperature. Notice that fat melting is relatively sharp between 30 and 45 degrees, while protein denaturation is more gradual, beginning around 40 degrees and continuing to 90 degrees. As proteins denature and fats melt, they reorganize into a continuous viscoelastic matrix. This network provides structural integrity while allowing flow, creating the characteristic stretchiness of melted cheese. Finally, we examine Maillard reactions. These non-enzymatic browning reactions occur between reducing sugars and amino acids at high temperatures, producing hundreds of flavor compounds. Our fourth question: why do the browned surfaces and interfaces between layers possess the most concentrated and complex flavors? The answer is that Maillard reactions are highly temperature dependent, with reaction rates doubling for every 10-degree increase. The interfaces, particularly the top surface and boundaries between layers, reach the highest temperatures of 150 to 180 degrees Celsius. The general reaction scheme, reducing sugar with amino group plus amino acid under heat with loss of water, yields hundreds of flavor compounds, including pyrazines, furans, and thiazoles. This exponential plot shows Maillard reaction rate versus temperature. Note the dramatic acceleration above 150 degrees. This surface at 180 degrees has a reaction rate nearly 50 times higher than the center at 120 degrees. This cross-section shows the distribution of Maillard reaction products, indicated by orange dots. The highest concentration occurs at the top surface and at pasta sauce interfaces, where temperatures exceed 150 degrees. The bottom layers show minimal browning. The products include brown pigments called melanoidins, which provide color, and volatile compounds such as 2-acetyl-1-pyrroline and 2-furfuryl-thiol, which contribute roasted, nutty, and caramelized aromas. Now let us integrate these phenomena. During baking at 180 degrees Celsius for 45 minutes, all three processes occur simultaneously and interdependently. This multi-process plot shows the time evolution of all three transformations. Starch gelatinization in blue begins immediately and reaches 95% completion by 30 minutes. Protein denaturation in green follows a similar but slower trajectory. Maillard reactions in red have a lag phase, then accelerate after 10 minutes. The challenge is achieving complete starch gelatinization and protein denaturation without excessive Maillard reactions, which can lead to burning and bitter flavors. The optimal baking time is typically 40 to 50 minutes at 175 to 185 degrees Celsius. Moisture plays a critical role by facilitating starch gelatinization, enabling protein mobility during denaturation, and moderating Maillard reaction rates. The sauce provides this moisture, which diffuses through the pasta sheets over time. Let us quantify the energy requirements. The total energy input must account for heating the mass, driving endothermic reactions, and evaporating water. The total heat is Q total equals mc delta T plus delta H reaction plus N delta H vaporization. The first term is sensible heat, second is reaction enthalpy, and third is evaporative heat loss. For a typical 3 kilogram lasagna, the sensible heat to raise temperature from 20 to 180 degrees is approximately 1.5 megajoules. Starch gelatinization adds 0.3 megajoules. Protein denaturation adds 0.2 megajoules. Water evaporation of 100 grams adds 0.2 megajoules. Total energy is approximately 2.2 megajoules. Our final question: what physical principles determine the optimal thickness of each layer to achieve uniform cooking and optimal texture? The answer involves two length scales. First, the thermal diffusion length, given by the square root of thermal diffusivity times cooking time, should be comparable to total thickness. Second, moisture must diffuse through pasta sheets in the available time, governed by Fick's law. The thermal diffusion length L thermal equals square root of alpha times T, approximately 3 to 4 centimeters for typical cooking times. This suggests total lasagna thickness should not exceed 4 to 5 centimeters. Moisture flux follows Fick's first law, J equals negative D times concentration gradient. The diffusion coefficient for water in pasta is approximately 10 to the negative 10 square meters per second, limiting practical pasta sheet thickness to 1 to 2 millimeters for adequate hydration. In summary, lasagna represents a fascinating multi-scale physical and chemical system. At the macroscopic scale, we observe layered heat transfer with thermal resistances in series. At the molecular scale, we have starch polymer hydration and crystalline melting, protein tertiary structure disruption, lipid crystal to liquid transition, and amino acid sugar condensation reactions. All these processes are thermally activated, with Arrhenius temperature dependence and characteristic time constants ranging from minutes to tens of minutes. Successful preparation requires maintaining temperatures in the range of 175 to 185 degrees Celsius for 40 to 50 minutes, ensuring complete starch gelatinization and protein denaturation while achieving optimal but not excessive Maillard browning. This final illustration summarizes our scientific understanding. Lasagna is not merely food, but an elegant demonstration of coupled transport phenomena, polymer physics, protein chemistry, and organic reaction kinetics, all orchestrated to produce a nutritious and flavorful meal.